The United States has just surpassed a drought record that has stood for 131 years. Yet there is an element to this story that is profoundly unsettling. The specific climate event anticipated to produce such conditions has not yet materialized. The primary trigger has not been pulled. What we are witnessing today is merely the prelude. Currently, 60% of the lower 48 states is experiencing drought. In Florida, 99% of the state is abnormally dry. The winter wheat crop is failing. And Lake Powell is nearing a critical threshold where it can no longer generate hydroelectric power. Cattle herds have dwindled to numbers unseen since 1952. All of this is unfolding while a super El Niño continues to gather strength in the Pacific. It raises a deeply concerning question. If the system is already this compromised before the main forcing event arrives, what will happen when it finally does? This is not a story that is winding down. It is accelerating. The drought is intensifying. The mountain snowpack has vanished, and reservoirs are receding at an alarming rate. All the while, the Super El Niño is still developing. The situation is so dynamic that it demands close observation, and here at Calm Space, we will be monitoring each development as it unfolds through its peak. The narrative is complex, and it begins with a strange disruption in the expected sequence of events, a record that was broken before its cause was ever set in motion. Something appears to be fundamentally misaligned with the historical timeline of the American climate. This isn't about a single storm, a single season, or even one anomalous year. It concerns the entire recorded history of the nation's climate patterns. As of the spring of 2026, the United States finds itself in the grip of the most severe drought documented in 131 years of continuous, instrument-based records. Yet, the very phenomenon that scientists expected to be the primary driver of this extreme aridity has not yet fully formed. It is a paradox that deserves a moment of reflection. The worst conditions on record have arrived before the main event. This is the central mystery we will explore. Every consequence we are about to discuss, the absent snowpack, the shrinking cattle herds, reminiscent of 1952, the reservoirs dropping toward levels that should not yet be possible, all flow from this single, seemingly impossible fact. The record was shattered before the trigger was fired. This account is not built on speculation, but on data, and the numbers themselves are genuinely cause for concern. The National Oceanic and Atmospheric Administration, or NOAA, curates what is known as the National Centers for Environmental Information Dataset. This is the definitive archive for American climate records, extending all the way back to 1895. That was the year when standardized weather instruments became widespread enough across the country to produce statistically sound national data. This provides a continuous chronicle of 131 years of readings, encompassing temperature, precipitation, and soil moisture for every month and season. In the first 3 months of 2026, covering January, February, and March, the United States registered its single driest start to a year ever recorded. This wasn't merely close to the old record. It broke a mark that had remained untouched since 1910. The fact that 2026 surpassed a record from 1910 makes the event all the more striking. In that era, the Wright brothers had only been flying for 7 years. There were just 46 states in the Union, and the instruments used to measure that historic drought were far less precise than those we rely on today. If anything, the 1910 measurement was likely an overestimation of the true dryness, given the wider error margins of the instruments at the time. The ability of modern, more accurate tools to register an even more extreme value today suggests the severity of our current situation is not being exaggerated. While a single metric can sometimes be misleading, What makes the spring of 2026 so difficult to dismiss is that it is not one measurement, but a convergence of every major indicator. All of them are pointing in the same alarming direction, creating a chorus of evidence that is hard to ignore. One of the most widely used tools in climate science for measuring drought is the Palmer Drought Severity Index, or PDSI. This is not just a simple measure of rainfall. It is an integrated model that considers precipitation, temperature, the capacity of soil to store and release moisture, and the atmosphere's demand for water. The result is a single number. Positive values indicate wet conditions, while negative values signify drought. The more negative the number, the more intense the drought. You can think of it as a running balance sheet for a region's water supply, where every hot, rainless week is recorded as a debit. In March of 2026, the national PDSI value was a staggering -7.85. April followed at -7.56. To place these figures in their proper context, one must look back to 1934, the absolute height of the Dust Bowl, to find more severe numbers. That was the era of John Steinbeck's times, the grapes of wrath, of immense dust storms that buried entire towns. That is the only historical frame of reference for what the PDSI is showing now, and even that comparison comes with its own unsettling caveats. Then there is the sheer geographic scope of the problem. As of the spring of 2026, an astonishing 60.92% of the contiguous United States, what scientists refer to as the lower 48, was officially in drought. Of that area, nearly 44% was classified in the severe to exceptional range. These are not vague classifications. Severe drought corresponds to likely crop losses, mandatory water restrictions, and widespread stress on livestock. Exceptional drought is the highest category on the scale, a level where federal disaster declarations become almost automatic and aquifers can begin to show multi-year damage. When nearly half the country is simultaneously experiencing these conditions, it ceases to be a regional weather problem. It begins to behave more like a continental system failure, revealing a fragility that extends across the nation. And this brings us back to the most difficult part of this entire situation to process. The climate-forcing event that most models anticipated would drive these extreme conditions does not yet fully exist. We are speaking of El Niño specifically, a potentially historic event that some models project could reach the status of a super El Niño. This would involve sea surface temperature anomalies in the central and eastern Pacific Ocean exceeding 2 degrees Celsius above normal, with some projections even suggesting they could surpass 3 degrees. According to leading ensemble forecasts, the probability of El Niño conditions developing by the middle of 2026 is approximately 61%. While this means it is more likely than not, it also confirms that the event has not yet happened. The system is already breaking records without its trigger. It is as if a boxer has been knocked down before the opening bell has even rung. That is the precarious position we find ourselves in today. The dryness we are witnessing is not the one we were warned would come. It is something else entirely, a precursor, a new baseline from which something far greater might emerge. If the forecasted trigger event, a super El Niño at the upper range of climate models, does indeed materialize, then our current experience is not the main story. It is merely the setup. In a field somewhere in Kansas, a farmer is looking at soil moisture levels that belong in late June, yet they are appearing in early spring. In the Colorado River Basin, a reservoir manager reviews projections that consistently yield numbers she finds difficult to accept. And in the Pacific Northwest, a wildfire planner studies snowpack maps, showing percentages so alarmingly low they fall outside the historical color coding of his software. None of these individuals required a formal forecast to know that something was deeply wrong. The land itself told them first. Yet, at a national level, we have not been fully attuned, because this particular disaster lacks a single, defining moment. There is no hurricane making landfall on camera. It is a crisis that does not announce itself with a sudden crash, but one that quietly, relentlessly deepens. This leads us to the question that should frame all that follows. If this is what the world looks like before the main event, what will the peak truly be like? There is a guiding principle in science. When multiple independent systems of measurement all point to the same conclusion, that conclusion gains a powerful weight that is difficult to dismiss. One can always dispute a single thermometer, question one set of data, or find methodological flaws in an individual study. But when three completely separate instruments, each using a unique approach to measure the same phenomenon, deliver the same answer at the same time and on the same scale, you are no longer confronting uncertainty. You are confronting reality. This is precisely the situation with the drought of 2026. It is worth examining each of these three systems, because understanding the nature of their agreement is more vital than any single number they produce. The first system offers the most direct evidence: precipitation anomaly data from NOAA. This is the raw measurement, detailing how much rain and snow actually fell compared to the historical average for a given period. There is no complex modeling or inference involved, just the simple, cumulative numbers from thousands of monitoring stations across the nation. For the period of January through March 2026, the data showed it was the driest such period since record-keeping began in 1895. The statement stands on its own, stark, and without any qualifying clauses to soften its impact. The second system is the Palmer Drought Severity Index, or PDSI, which we have mentioned before. This integrated water balance model asks a more nuanced question. It does not just measure how much water fell from the sky, but assesses how much moisture the land truly has available. To do this, it must account for how much water the atmosphere demands back through evaporation and plant transpiration. This is a critical distinction, because the same lack of rainfall that might cause a moderate drought in a cooler year can produce a severe one in a warmer year. The PDSI integrates temperature directly into its calculation. So, when it registered a value of negative 7.85 inches March of 2026, it was signaling that the combination of low precipitation and high atmospheric demand had created a soil water deficit, second only to the absolute worst month of the most devastating drought in America's recorded history. Our third system, the United States Drought Monitor, USDM, takes an entirely different approach. Instead of relying solely on physical water balances, the Drought Monitor employs a multi-indicator methodology. It incorporates data on precipitation, soil moisture, stream flow, and groundwater levels, but also includes vegetation, health indices, and, crucially, expert input from local observers on the ground. It then classifies regions into 5 distinct categories: abnormally dry, moderate drought, severe drought, extreme drought, and exceptional drought. This classification is based on observable impacts to agriculture, water supplies, and ecosystems. Of the 3 systems, it is the most operationally grounded, as it moves beyond model outputs to ask what is actually happening to crops, reservoirs, and rivers. In April of 2026, all 3 systems delivered the same verdict in unison. The precipitation record declared it the driest period ever documented. The PDSI reported a soil water deficit, second only to the Dust Bowl era. And the Drought Monitor revealed that 60.92% of the lower 48 states were in drought, with nearly 44% experiencing conditions in the severe to exceptional range. Not a single one of these metrics offered a different story or a more hopeful narrative. Their convergence was absolute. This unanimity is profoundly important because, in past droughts, it was common for these metrics to disagree. A regional drought might cause the Drought Monitor's numbers to spike in one area, while national precipitation anomalies remained normal. A hot, dry spring in the southwest could elevate the PDSI there without significantly affecting the drought monitor's readings in the northeast. This divergence between metrics is normal because drought has historically been a local or regional phenomenon. What is occurring now is something climatologists refer to as continental coherence. The drought is acting as a single, unified system across the entire contiguous United States at the same time. This is not how drought normally behaves. This is something new. There is another critical concept to grasp. What happens when the scale of an event pushes against the very limits of the system designed to measure it? Climate scientists call this metric saturation. The drought monitor's most severe classification, D4 or exceptional drought, was designed to describe conditions that occur with great rarity, perhaps affecting 5 to 10% of the country in the most extreme circumstances. But when nearly a quarter of the lower 48 falls under this classification, the system itself begins to lose its descriptive power. The very meaning of our words begins to fail us. Words like severe and exceptional were calibrated against a different baseline, a world of the past. They do not fully convey the reality of what is happening when they apply to nearly half the country simultaneously. This is one reason why the story is not penetrating our collective awareness as it should. The language of drought was created for a world where these thresholds were truly exceptional. In a world where they are becoming the baseline, the words no longer trigger the alarm they were designed to. When every new event sets a record, the idea of a record loses its meaning. When exceptional drought is widespread, the word exceptional no longer sounds exceptional. The communication system has become saturated, just like the measurement system. And there is another dynamic at play here. Slow disasters, like drought, operate on a fundamentally different timeline than acute ones, such as earthquakes or hurricanes. A sudden catastrophe has a clear focal point, a landfall, an epicenter, a singular moment and location that commands our attention. Drought, however, offers no such clarity. It is a quiet accumulation, a debt that grows in silence, day after day, week after week. The bill only comes due when it is far too late, manifesting as failed crops, depleted reservoirs, and fire seasons that ignite as early as February. This phenomenon, where a developing crisis fails to register as one because no single day feels dramatically different from the last, is what scientists call slow disaster invisibility. The Great Drought of 2026 inches, the United States, stands as a stark illustration of this principle. Its roots trace back to at least the autumn of 2025, with key metrics worsening for months. Yet, because there was no single day the drought happened, it has simmered in the background of public awareness instead of commanding it. The challenge is magnified by its sheer spatial scale. When 60% of a country is simultaneously in drought, there is no unaffected elsewhere from which to observe the crisis. When drought is everywhere, it risks becoming the new normal, invisibly and rapidly. This cognitive normalization may be the most insidious danger of the current situation. Within this sprawling story, one particular corner illustrates these dynamics with exceptional clarity. The convergence of metrics, the counterintuitive geography, and the failure of our usual language to capture the scale of the event. The heart of this narrative is not found in the arid Southwest, where drought is a familiar, if unwelcome, guest. Nor is it in the parched Great Plains, where generations of wheat farmers have learned to watch soil moisture monitors with vigilance. Instead, the most telling chapter unfolds in a state that seems entirely out of place in this story. It is a state most people associate with abundant rain, deep humidity, and the reliable daily rhythm of thunderstorms rolling in from the Gulf of Mexico. It is a place that receives more annual rainfall than much of England. Yet, Florida is now in the grip of its worst drought in 15 years. This is not a story about one corner of the state. It encompasses effectively all of it. a fact that fundamentally changes everything. A glance at any drought monitor map from April of 2026 reveals a startling anomaly in the southeastern United States. On a typical map, Florida simply should not look like this. The state's geography, positioned between the Gulf of Mexico and the Atlantic Ocean, normally ensures a constant delivery of atmospheric moisture to the peninsula. It is a humid, subtropical climate, so reliable that its afternoon thunderstorms are a feature of daily life. Used by tourists to schedule their visits to theme parks, the pattern is a cornerstone of the region's identity. You head indoors when the clouds gather around 2 in the afternoon, wait for the rain to pass, and then resume your day. That is simply how Florida's weather works. Except in April of 2026, that familiar cycle had vanished. An astonishing 98.99% of Florida was officially in a state of drought. Not half, not 70%, but nearly the entire peninsula. The data paints an even grimmer picture. Half of the state was classified as being in extreme drought, the D3 category, which is just one step from the most severe level. More alarmingly, roughly 22% had crossed into exceptional drought, or D4, the highest classification the drought monitor employs. This designation is reserved for conditions that are historically rare, economically devastating, and ecologically disruptive, even in states that are accustomed to dry spells. For Florida, a state whose very biology is woven from water, its cypress swamps, its springs, its river systems, this was an internal catastrophe. The question it raises is profound. What atmospheric force could be powerful enough to so completely subvert a region's fundamental climate? The strangeness of Florida's predicament is not just a local humidity anomaly. It is a key symptom of a much larger atmospheric configuration that helps explain what is occurring across the entire country at once. The mechanism at the heart of this geographically broad drought is known as the Bermuda High. This is a semi-permanent system of high pressure that normally sits over the western Atlantic Ocean. In its typical position, its circulation is immensely beneficial, pulling warm, moisture-rich air northward from the Gulf of Mexico and the Caribbean into the southeastern United States. This is the atmospheric engine that fuels those iconic afternoon thunderstorms and keeps Florida's landscape wet. But everything changes when the Bermuda High expands and shifts its position westward, pushing its boundaries inland. When this happens, it creates a dome of high atmospheric pressure over the southeast that re-engineers how the region's atmosphere behaves. High-pressure systems are defined by what is known as atmospheric subsidence, which is air sinking from above. As this air descends, it gets compressed and warms adiabatically. Sinking air is the enemy of cloud formation. Clouds need moist air to rise, cool, and allow water vapor to condense. When the atmosphere is actively sinking, that entire process is suppressed. The moisture that would typically be lifted into thunderstorms is held down, while the sinking, warming air simultaneously increases the evaporative demand on the surface, pulling moisture out of the soil, vegetation, and water bodies, instead of depositing it as rain. In effect, the westward expansion of the Bermuda High places a lid on Florida's entire weather system. The moisture is still there, lingering offshore where the Gulf remains warm, but the atmospheric circulation that would normally transport it inland has been rerouted. The result, observed through late 2025 and the first half of 2026, has been a phenomenon hydrologists are calling a hydrological inversion. This is a paradoxical state in which a region climatologically defined by its surplus of water begins to behave like an arid system. It's a fundamental reversal of the natural order. This inversion places extraordinary stress on wet-adapted ecosystems, a level of pressure that ecosystems in drier climates might normally absorb without crisis. The region's infrastructure is profoundly unprepared. In the American West, where drought is an endemic feature of the climate, There are vast reservoirs designed to hold several years' worth of water, intricate legal systems for allocating scarcity, and agricultural practices calibrated for low rainfall. In Florida, none of that architecture exists for the simple reason that it was never needed before. The implications of this vulnerability are vast, and one of the most immediate dangers concerns the escalating risk of wildfire. When a typically moist ecosystem experiences drought, the result can be uniquely perilous, even more so than in a chronically arid land. Ecosystems in dry regions are adapted for fire, with sparse vegetation that has evolved to withstand such conditions. But subtropical Florida is a world apart, defined by its dense, waterlogged landscapes. Here, palmetto scrub, pine flatwoods, and cypress swamps are not naturally prone to carrying fire like the shrublands of the West. When this lush vegetation dries out, however, it becomes an immense source of fuel in environments ill-equipped to manage it. Communities are not hardened against fire, and emergency responders are unaccustomed to operations on such a scale. This phenomenon is not isolated to Florida. During this same period, nearly 99% of the entire Southeast is gripped by drought, with Georgia, South Carolina, Alabama, and Mississippi all caught in the same pattern. The expansion of the Bermuda High has created a climatic regime across the whole southeastern United States that seems to defy the region's fundamental climatology. And here, a crucial thread emerges. All of this is unfolding times the arrival of El Niño. The atmospheric pattern driving these conditions is a precursor, a phenomenon that has appeared in the absence of the very forcing event that climate models predicted would cause the worst impact. This is not the drought that forecasters warned of. It is the drought that came before it, raising an unnerving question. What will happen to Florida when El Niño finally does arrive? When atmospheric patterns shift once more, and the Bermuda High responds to changing sea surface temperatures in the Pacific, the consequences are yet unknown. But to understand the full scope of the crisis, we must turn our attention elsewhere. We must travel west, to mountains that should be draped in white deep into April, and confront a different kind of water failure, one that operates on a completely different timescale than rainfall. It is a story about the snowpack that is no longer there, and why its absence means that for vast portions of the American West, the water crisis for an entire year is already decided before the summer has even begun. Part 4. The West without snow. There is a fundamental concept in hydrology, one that often goes unnoticed by the public, but which governs the water supply for tens of millions of Americans. It is the idea of snowpack as a natural water savings account. Each winter, precipitation in the mountains does not simply run off. It gathers as snow, compressed and preserved in the high elevations, forming a vast reservoir made not of concrete, but of frozen water. As the warmth of spring and summer arrives, this snowpack melts in a slow, continuous release. This process feeds rivers, streams, and reservoirs at the precise time of year when agricultural, municipal, and industrial demand is at its peak, and natural rainfall is at its lowest. It is a brilliant, natural delay mechanism. The Great Mountain Ranges, the Rockies, the Sierra Nevada, the Cascades all serve as enormous elevated water towers, smoothing out the stark difference between the wet and dry seasons for the entire western half of the United States. When this elegant system functions as intended, it is almost invisible, but when it fails, the consequences are both swift and severe. On the 1st of April, 2026, a staggering event unfolded. 8 western states simultaneously registered new all-time record low snowpack values. Not just low, but the lowest in recorded history. This occurred in Arizona, Colorado, Idaho, Nevada, New Mexico, Oregon, Utah, and Wyoming all at once. This was no regional anomaly or localized weather pattern. It was a crisis spanning the full geographical breadth of the American West, from the Mexican to the Canadian border, from the Pacific coast to the continental divide. The same historical extreme, measured on the same calendar day across the entire region. The measurement that truly matters in this context is snow water equivalent, or SWE. This metric reveals not merely the depth of the snow, but the actual volume of water locked within it. A fluffy, cold snowpack has a low SWE, while a dense, wet snowpack has a high one. The measurement taken on April 1st is traditionally the most critical, as it marks the peak of snow accumulation for most western mountain ranges before the spring melt begins. For this reason, the April 1st SWE figure is often the single most important number for forecasting the water supply for the dry season ahead. The data from Oregon speaks volumes. On the 1st of April 2026, its statewide snowpack stood at just 12% of the historical median. This was not a 12% reduction from normal. It was 12% times normal, meaning 88% of the expected water storage was simply missing. Other states fared only slightly better, with Colorado and Utah reporting values in the 20 to 30% range, and Wyoming and Idaho not far above that. Critically, the timing of the melt revealed an even more alarming dimension to the crisis. By the time these record low numbers were recorded, 75% of the SNOTEL monitoring sites, the automated, high-elevation sensors that track snowpack across the West, had already reported their snow was completely gone. This occurred more than a month earlier than the historical average meltout date, a detail with enormous consequences. When a snowpack melts a month ahead of schedule, you don't just lose a month of gradual, usable water. The entire smoothing function of the system is lost. Instead of a slow, sustained release of water through June, July, and into August, the landscape receives a brief, intense pulse of meltwater in March and early April. This pulse is often too fast and too early for reservoirs to capture effectively, and it is followed by an unnerving silence, dry riverbeds, and plummeting reservoir levels for the rest of the season, precisely when demand reaches its peak. The Colorado River Basin provides a stark illustration of this crisis, particularly the role that temperature played. The basin, which drains parts of Wyoming, Colorado, Utah, New Mexico, Nevada, Arizona, and California, is the lifeblood for roughly 40 million people. In the spring of 2026, this region recorded temperature anomalies of positive 13.7 degrees Fahrenheit above the historical average. A departure of nearly 14 degrees above normal has profound effects. At such temperatures, precipitation that would have historically fallen as snow instead arrives as rain, which runs off immediately without building any storage in the mountain reservoir. Furthermore, any snow that does manage to accumulate melts not only earlier, but with far greater speed. The entire melt pulse becomes compressed into an ever shorter window, rendering this vital natural resource almost unusable. The increased evaporation from soils and surface water is not a random occurrence. It accelerates according to a well-understood physical relationship. For every single degree Celsius of warming, the atmosphere's capacity to hold water vapor expands by approximately 7%. This means its power to draw moisture from the land and water below increases by that same amount. In practical terms, an anomalous warmth of 13.7 degrees Fahrenheit means the Colorado River Basin's natural water storage system is not just experiencing a low year. It suggests the system is fundamentally compromised, with effects that will unfold on timescales far longer than a single season. High in the mountains, the very permafrost that stabilizes alpine soils is transforming. The plant communities that help regulate the water cycle at high elevations are under profound stress. Consequently, the established relationships between runoff timing and volume data used for decades by reservoir managers at Glen Canyon and Hoover dams can no longer be trusted as reliable guides for the river's flow. And it is here that the central, troubling question of this entire story returns to the forefront. All of these cascading problems, the absent snowpack, the extreme temperature anomalies, the early melt, and the compromised water storage are unfolding times before times the arrival of El Niño. This is the very forcing event, the specific climate driver that models had indicated would produce the most severe impacts on the water supply of the American West. That driver is still gathering strength. The El Niño Southern Oscillation, or ENSO, is currently in a state of transition, moving from neutral conditions toward a full El Niño, with its peak development anticipated for the latter half of 2026. The snowpack catastrophe we are witnessing now occurred when the Pacific Ocean was, in ENSO terms, only beginning to shift. This leads to a stark conclusion. The water crisis facing the American West in 2026 is not some forecasted risk. It is a reality that was locked into place back in February and March, when the snow that should have been accumulating simply never fell. No amount of summer rainfall can undo the absence of a winter snowpack. A hurricane making landfall on the Gulf Coast cannot refill the Colorado River. The water budget for the entire year for hundreds of millions of acres of Western agriculture, for dozens of cities, and for the hydroelectric generation that powers millions of homes was written in the negative on mountain slopes that should have remained white deep into May. The system is not merely dry. It is showing signs of structural failure. The question is no longer whether this failure will have consequences. The question now is which consequences will manifest first, how rapidly they will arrive, and in what order they will appear. When systems begin to fail across so many dimensions at once, precipitation, snowpack, soil moisture, and surface water, the effects do not form a neat line. They interact and amplify one another. What begins as a drought evolves into something far more complex, more interconnected, and ultimately more difficult to manage than any crisis affecting a single dimension. This brings us to the core of the issue, a pattern that requires a deeper explanation. A fundamental question has been lingering beneath every observation we have examined so far. Why? Why is 60% of the country simultaneously dry? How can 8 western states all be hitting record low snowpack levels at the same time? And why is Florida, a subtropical, ocean-bordered state that is normally drenched in rainfall, sitting at the highest level of the drought severity scale? A drought this geographically coherent, this simultaneous across regions with completely different climates, does not simply arise from a deficit of rain. It points to an atmospheric configuration, coordinating dry conditions on a continental scale. To understand this configuration, we must take a brief excursion into atmospheric physics, a concept that may sound complex but is, once visualized, remarkably intuitive. The atmosphere is not a static entity. It is in constant motion, with vast, continent-spanning wave patterns, called Rossby waves, propagating through the upper troposphere. This is the layer of the atmosphere where our weather systems are born and live. These waves have peaks, known as ridges, and troughs. The ridges represent high-pressure systems, where air descends, warms, and dries. The troughs, in contrast, represent low-pressure systems, characterized by rising, cooling, and moisture-rich air. In a healthy, mobile atmosphere, these Rossby waves travel eastward, cycling through different regions and bringing the alternating periods of wet and dry weather that average out to what we consider normal conditions. But what happens when this elegant atmospheric dance falters? Rossby waves can slow down, and in extreme cases, they can come to a near standstill. When a ridge, a high-pressure peak in the wave pattern, locks itself into place over a region for weeks or even months, the atmosphere essentially stalls. The normal cycling of weather ceases. Systems that would typically move through the area, bringing precipitation, are instead deflected around the stationary ridge. Moisture is rerouted away from the locked region. All the while, the persistent subsidence within the ridge forces air to keep sinking, warming, and drying out the land below for an extended period. Climatologists have a name for this phenomenon, a blocking high. When one is strong and persistent enough, it can drive a drought of such depth and geographic scale that normal weather variability alone cannot explain it. Looking back at the atmospheric conditions over North America in late 2025 and through the first half of 2026, the data reveals precisely this kind of persistent ridging. A particular Rossby wave configuration parked a dominant high-pressure system over much of the contiguous United States for an extended time. This pattern suppressed precipitation, rerouted moisture from the Gulf, and created the perfect conditions for a drought to establish itself not just in one region, but across the entire country at once. The expansion of the Bermuda High, which we discussed in the context of Florida's drought, is merely one part of this larger pattern. It is the eastern expression of a vast ridge system that extended much farther west and north than its usual territory. This phenomenon is not just theoretical. Recent science has begun to give it a name and a framework. Researchers, including a 2021 study by Hahn and colleagues, have identified what they term low-phase speed wave packets. These are, in essence, extremely slow-moving or nearly stationary atmospheric wave patterns that can maintain their coherent structure for much longer than traditional Rossby wave theory would predict. It is these slow waves that create the kind of persistent, locked-in atmospheric regimes that are capable of driving the most severe, multi-month droughts on record. This leads to a final, critical connection, a hypothesis that links our warming world to these increasingly stubborn weather patterns. There is a growing body of evidence, still considered somewhat speculative, but becoming increasingly difficult to ignore, that the weakening of the jet stream itself may be making these slow, stuck wave patterns more common. This weakening is potentially connected to the reduced temperature gradient between the equator and the poles, a change driven by amplified warming in the Arctic. The logic follows that a more sluggish jet stream produces more persistent blocking patterns. More persistent blocking, in turn, produces more prolonged and severe droughts. And this provides the crucial connection back to the central story of a continent in crisis. A central puzzle of this drought is how it managed to form with such geographic coherence long before the arrival of El Niño. The answer lies in a pre-existing atmospheric pattern, a kind of structural lock that set the stage. A persistent ridge of high pressure, an atmospheric wall, stalled over the continent, systematically deflecting moisture-rich air away from the land. This provided the perfect scaffolding for record-breaking dryness to take hold. Most remarkably, this all occurred during a period that forecasters considered a neutral transition phase in the El Niño Southern Oscillation, a time when no major climatic driver was expected. It raises a critical question. If the powerful influence of El Niño wasn't the cause, what was? The El Niño forcing did not create this event. It is merely poised to amplify it. The drought was already present, already at a historic scale, built upon an atmospheric foundation that, on its own, generated the most severe conditions in 131 years of record-keeping, entirely without any forcing from the tropical Pacific. While drought and heat are distinct phenomena, they are locked in a profound recursive relationship, and this connection makes the situation in 2026 fundamentally different from any major American drought that has preceded it. At the heart of this dynamic is a thermodynamic principle described by the Clausius-Clapeyron equation. The mathematics are complex, but the core concept is essential. For every 1 degree Celsius rise in air temperature, the atmosphere's capacity to hold water vapor increases by about 7%. This means warmer air is effectively thirstier, possessing a greater power to draw moisture from the soil, from water bodies, and from vegetation through evaporation. The consequence of this physical law is that an identical rainfall deficit that might have led to a moderate drought in a cooler past now results in severe or exceptional drought. The warmer atmosphere simply demands a greater share of the water it delivers, changing the very rules of the game. The first quarter of 2026 provided a stark illustration of this new reality. The United States endured not only its driest January through March on record, but also temperatures that were significantly above historical averages. What makes this so telling is that it occurred during a La Niña phase, a period that typically brings cooler conditions to much of the nation. The fact that temperatures stubbornly remained above normal, even during a natural cooling cycle, speaks volumes about the underlying shift in our planet's thermal baseline. It suggests the background warming trend has progressed so far that even powerful, naturally occurring cooling influences can no longer pull temperatures down to what was once considered normal. Adding another layer of complexity is a factor that, while still debated scientifically, is sparking intense discussion. In January 2020, the International Maritime Organization enacted new regulations for global shipping, leading to a dramatic reduction in sulfur aerosol emissions. In the atmosphere, these sulfur aerosols serve as nuclei for cloud formation and have a known cooling effect, reflecting solar radiation back into space. Some researchers, including James Hansen and his colleagues, have proposed that removing these aerosols has effectively unmasked a degree of warming that was always present due to greenhouse gases, but was being partially counteracted. Their hypothesis suggests we may now be witnessing an acceleration in surface warming that exceeds what standard IPCC models had projected. It is crucial to note that this interpretation is not universally accepted, and it is not fully integrated into consensus projections. However, the fundamental physics is sound. Sulfur aerosols do cool the climate, and we did drastically reduce their emission in 2020. The great uncertainty lies in the magnitude of the resulting warming. This possibility, that the background warming is even higher than mainstream models accounted for, is a critical piece of context. But what is not debated is the direct, accelerating effect that heat has on drought. This atmospheric thirst can be quantified using a tool known as the Evaporative Demand Drought Index, or EDI. Throughout the spring of 2026, EDDI values across the American West and Southeast have reached historically extreme levels, a direct result of the combination of low precipitation and exceptionally high temperatures. This potent combination of heat and dryness gives rise to a phenomenon researchers call a flash drought. This is a pathway of drought development that can escalate conditions from near normal to severe in a matter of weeks, a stark contrast to the months-long timeline of classical droughts. Such rapid intensification is especially devastating for agriculture, as it outpaces the ability of both crops and farmers to adapt. Often, by the time soil moisture monitors signal a critical problem, the stress on crops has already surpassed a point of no return, locking in significant yield losses. This new breed of drought doesn't just arrive, it ambushes the landscape. All of these factors converge on a central point. The heat amplification makes the current drought far more severe for any given level of rainfall deficit than a comparable event would have been in a cooler climate. The same shortfall in precipitation that caused the historic droughts of the 1950s or 1980s would, in the warmer atmosphere of 2026, create far worse soil moisture deficits, more dramatic reservoir depletion, and more intense stress on crops. The entire system was effectively pre-amplified before El Niño even entered the scene. The background thermal state of the atmosphere is already causing this drought to punch well above its weight, magnifying its physical impacts across the board. Yet, the atmospheric story is only half of the equation. We have not yet considered the role of the soil itself, which is not merely a passive victim in this narrative. The ground beneath our feet is an active participant, and once it crosses certain thresholds, it begins to drive the drought, rather than just enduring its effects. Most of us tend to think of drought in simple terms, like a bank account for soil moisture. Rain makes deposits, while evaporation and plants make withdrawals. When the balance reaches zero, you are in a drought, and when the rains return, the account is replenished. This analogy, however, is misleadingly simple. The true relationship between the soil and the atmosphere is less like a bank account and more like a thermostat, a feedback system. Understanding this shift in perspective is key to grasping the self-reinforcing nature of the current crisis. It explains why the drought continues to deepen, even when the external driving factors remain unchanged, and why it is accelerating more rapidly than historical droughts at similar stages. The soil, it turns out, has its own role to play in perpetuating its own dryness, a concept we must explore to see the full picture. When soil holds sufficient moisture, a large amount of the sun's incoming energy is used for evapotranspiration. This is the combined effect of water evaporating from the ground and transpiring from the leaves of plants. This transformation of liquid water into vapor requires energy, absorbing heat that would otherwise warm the land and the air directly above it. In this way, damp soil and thriving vegetation function as a form of natural air conditioning, moderating temperatures and sustaining humidity. Crucially, they also feed moisture into the lower atmosphere, which can then condense to create clouds. These clouds, in turn, reflect solar radiation, providing further cooling for the surface. Now, imagine that moisture is gone. With no water in the soil or plants, the sun's energy is no longer consumed by evapotranspiration. Instead, it is converted directly into sensible heat, which warms the surface and the air. Temperatures begin to spike. The boundary layer, the lowest kilometer or so of the atmosphere, grows hotter and more turbulent. As the humidity that normally seeds clouds plummets, the clouds themselves fail to form, removing their cooling shade and potential for rain. This allows even more solar energy to strike the surface unimpeded, driving temperatures higher and depleting any remaining soil moisture even faster. Researchers, including Morales and his colleagues, have termed this phenomenon soil, moisture, atmosphere coupling. It is a feedback loop where dry ground actively makes the atmosphere above it drier, suppressing the very precipitation it needs. The soil is no longer just a passive victim of the drought. It has become an active participant. Once this feedback cycle is engaged, the drought system becomes partially self-reliant. It can persist and even intensify without the original external trigger, such as a blocking high-pressure system or lack of rainfall, needing to continue with its initial force. The drought, in a sense, begins to generate its own momentum. This process is further amplified by vegetation. When plants experience severe water stress, they close their stomata, the tiny pores used for gas exchange, as a survival mechanism to conserve their limited internal water. But in doing so, the stressed vegetation ceases to release moisture into the air. This reduction in transpiration lowers local humidity, further inhibiting the formation of clouds. In its attempt to save itself, the plant life inadvertently strengthens the very conditions that threaten its existence. This effect scales dramatically, from the microscopic to the continental. A single water-stressed field closes its stomata. A parched watershed covering thousands of square kilometers reduces its collective transpiration. And a drought-stricken continent, like the one covering 60% of the lower 48 states in 2026, generates a measurable suppression of moisture recycling across an immense territory. The drought of 2026 has grown so vast that its own surface effects are altering atmospheric conditions over a substantial portion of North America. In a very real, physical sense, it is now helping to sustain itself. There are other, slower feedback pathways that compound the problem through vegetation die-off and disruptions to the carbon cycle. As forests and grasslands endure prolonged, severe drought, plant mortality rises. Dead vegetation cannot transpire water. It accumulates as dry fuel for wildfires, and it no longer captures carbon through photosynthesis. The carbon that a stressed ecosystem fails to sequester remains in the atmosphere, adding to the greenhouse effect that drives further warming. Some afflicted regions can even transform from carbon sinks into net carbon sources. This represents a feedback from climate stress back to the forces driving climate change, a process that unfolds more slowly than moisture feedbacks but is just as potent. The wildfire feedback then reinforces all of these effects. When drought-stressed vegetation burns, it instantly releases its stored carbon. The fire eliminates the cooling effect of living plants, darkens the land surface to increase solar absorption, and completely removes the transpiring plant community for years or even decades. It becomes clear that fire and drought are not two separate events, but rather two expressions of the same underlying crisis. What makes the spring of 2026 so deeply concerning from this perspective is the sheer duration over which these soils have been drying. This is not a 6-week dry spell after a normal winter. For many parts of the western United States, the soil moisture deficit has been accumulating for years. It is all part of a much longer pattern, one that the science of soil-atmosphere coupling helps us understand. And that longer pattern has a name, a research record stretching back 1,200 years, and a conclusion that is difficult to contemplate without a profound sense of unease. In 2022, a study published in the journal Nature Climate Change, led by researcher Park Williams, should have fundamentally altered the public conversation about drought in the American Southwest. The research team used tree ring records, the annual growth rings that act as a biological archive of regional temperature and moisture, to reconstruct drought conditions across the region for the past 1,200 years. Their conclusion was stark. The two-year span from 2000 to 2021 was the driest such period in that entire 1200-year record. It was drier than any extended drought in the 1600s, the 1500s, or any period since the late 800s. Critically, the team estimated that approximately 42% of the severity of this modern drought was directly attributable to anthropogenic warming. Nearly half of its intensity was not caused by natural variability or ocean cycles, but by human-caused climate change. This was the signature of the Southwest megadrought, a phenomenon amplified by our own actions. This context changes everything about the events of 2026. The conditions being measured are not a sudden, severe departure from the norm. Instead, they represent a continuation, an intensification, of a megadrought that has been underway for more than 2 decades. The drought did not begin now. It never truly ended. What we are witnessing is the megadrought entering a new phase of intensity, supercharged by a thermal background warmer than at any other point in the entire 1200-year tree ring record. A comparison to the megadroughts of the 1500s is both instructive and frightening. That earlier drought lasted for multiple decades and was driven primarily by natural variations in Pacific sea surface temperatures. This raises an unnerving question about our current predicament, which is amplified by forces far beyond natural cycles. A historical megadrought on the Colorado Plateau was so extreme that it may have played a role in the decline of several Native American agricultural societies. By any measure, it was a catastrophic period. Yet, it occurred within a climate that was, on average, about 1 degree Celsius cooler than our own. This seemingly small temperature difference is critical. In a cooler world, a lack of rainfall creates a less severe drought, as the atmosphere exerts a weaker pull on available surface water. Fast forward to the climate of 2026, and the equation has fundamentally changed. Due to temperature amplification, any shortfall in precipitation now strips moisture from the soil with far greater speed and intensity than a similar deficit would have in the 1500s. This reveals the core of the modern crisis, the dual forcing of drought. While historical events were driven by a single factor, a reduction in rainfall, today's droughts are subjected to a second compounding pressure: a relentless increase in evaporative demand, driven by modern warming. Where past mega-droughts faced one challenge, the current one faces two, and their combined effect is not merely additive, but multiplicative. Adding to this concern is emerging research that poses a disquieting question. What if the aridity is not temporary? Some studies suggest that the decline in precipitation itself could be evolving into a permanent structural characteristic of the Southwest's climate, rather than a cyclical downturn that will naturally reverse. While this remains a subject of intense scientific discussion, the implications are profound. If this hypothesis is correct, then our very understanding of drought recovery in the American Southwest may be obsolete. Recovery, by its nature, suggests a return to a prior state, a familiar baseline. But if that baseline has permanently shifted toward a drier reality, then there is nothing to recover to. All that remains is the new, arid normal, and the uncertain future it heralds. This framework provides the necessary context for interpreting the alarming record set in the spring of 2026, the shattering of a 131-year precipitation record, the historic lows in snowpack, and the depletion of major reservoirs are not random, isolated events occurring in a stable system. Instead, they must be seen as the latest manifestations of a systemic, multi-decade transformation that is now gathering speed. This acceleration is occurring just as another powerful climate driver, a super El Niño, enters the stage. The convergence of this mega-drought with a major El Niño event is not a simple case of misfortune. It represents the dangerous compounding of vulnerabilities that have been accumulating for decades. The consequences of this convergence are no longer a matter of future speculation. They are tangible and immediate. They are measured in the parched wheat fields of Kansas, in the struggles of cattle ranches, in the falling water levels of reservoirs, and on the sprawling maps of wildfire containment lines. A chain reaction has been initiated, and the critical question now is not if it will continue, but how far it will ultimately extend. In a Kansas wheat field during April of 2026, the signs of agricultural collapse are unmistakable, visible even without scientific instruments. The fields simply look wrong. The color is faded, the stands are thin and patchy. Where a dense green canopy should cover the earth, there are only sparse, stressed plants whose growth has been arrested weeks before it should have been. It is a silent, visual testament to a deepening crisis. The hard data from the USDA's weekly crop progress reports confirms this grim visual assessment. By the end of April 2026, a mere 31% of the nation's winter wheat crop was classified as good to excellent, the two ratings that typically signal a healthy harvest. In Kansas, the country's leading producer of winter wheat, the situation was even more dire, with the majority of its acreage falling into the poor or very poor categories. These condition ratings were on a trajectory toward the lowest points documented since the major droughts of the early 2000s. The consequences for the harvest are staggering, with regional models forecasting yield losses as high as 31% below the 5-year average. In response, plantings have plummeted to their lowest extent since 1919, as many farmers, facing soil too dry for germination, chose not to plant at all, or simply abandoned fields that had already failed. The economic calculus of whether to even attempt to save a dying crop led many to the same conclusion: to walk away. The reason for this widespread failure is written in the soil itself. Across vast stretches of Texas, Oklahoma, Colorado, and Kansas, soil moisture percentiles provided the stark explanation. In the vital root zone, moisture levels relative to the historical average had fallen into the lowest 5 to 10%. These are not numbers that merely stress a crop, they are numbers that can kill it. Once available water drops below a certain threshold, a a plant can no longer pull enough moisture to function, and the process of evapotranspiration effectively ceases. At this point, the crop enters a state of terminal stress. The damage becomes irreversible, locking in yield losses during critical growth phases that no amount of future rain can undo. This situation highlights a concept in agricultural science known as the invisible crop failure phase. This is the period when irreversible, drought-driven yield loss has already been sealed by soil conditions, but the widespread, visible evidence has not yet caught up. It is a phase of unsettling disconnect. The crop has, for all practical purposes, already failed. The farmer understands this, and the soil probe confirms it. Yet, satellite imagery may still show green fields. Commodity markets have not yet factored in the full scope of the loss, and the broader news cycle has not yet grasped what agronomists already know. This invisible phase can persist for weeks, right up until the combines at harvest time provide the final, undeniable proof. For large portions of the wheat crop, the spring of 2026 appears to be deep within this phase. The damage is already done. The only remaining question is one of magnitude: how severe the final yield deficit will be, and whether this shortfall will intersect with global supply issues to impact the price of food for everyone. A final critical dimension to this crisis is the question of irrigation. For farmers in the southern plains, the lifeline during times of drought has always been the Ogallala Aquifer. This immense underground reservoir, one of the largest on the planet, lies beneath roughly 174,000 square miles of the central United States. For decades, however, this vital resource has been in a state of steady decline, with water being extracted for irrigation far more rapidly than it can be replenished by rainfall. In past droughts, drawing from the Ogallala provided the crucial buffer that saved plains agriculture from total collapse. But in an era of dual forcing drought, the question is whether this already strained buffer can withstand the unprecedented demand now being placed upon it. For decades, the water table of the aquifer has been receding by 1 to 3 feet per year in its most heavily used regions. This slow, persistent decline has had a dramatic effect. In some parts of Texas and Kansas, the saturated thickness of this vital underground reservoir has been diminished by 50% or more compared to its historical levels. The buffer that protects against dry years is now dangerously thin. This raises a critical question. What happens when a severe drought strikes an already depleted resource? The answer is that drawing water to solve the short-term emergency only accelerates the long-term structural problem, creating a perilous feedback loop. The consequences of this water deficit ripple outward, extending far beyond American consumers. A 31% reduction in the US. Winter wheat yield is not a self-contained event, because the United States is one of the world's primary wheat exporters. Any disruption to its supply chain sends shockwaves through global grain markets, with effects that are felt most intensely in nations dependent on imports. When American wheat production declines sharply, global prices rise. The populations who feel this increase most acutely are those already spending the highest portion of their income on food communities in sub-Saharan Africa, South Asia, and the Middle East. It is a stark reminder that a drought in Kansas can have measurable humanitarian implications in Cairo and Karachi, a connection that is often underappreciated in domestic conversations about American agriculture. But the story of the grain does not unfold in isolation. A parallel signal is emerging from the livestock industry, one that in some ways provides an even more telling indicator of the drought's depth and its likely duration. This is because livestock, unlike annual crops, cannot simply be replanted once conditions improve. The recovery of a herd is a far more complex and lengthy process. In January of 2026, the USDA published its annual cattle report, which contained a number that did not receive nearly the attention it warranted. The total cattle and calf inventory in the United States stood at 86.2 million head, This figure represents the lowest cattle population in the nation since 1952, a span of 74 years. One has to look back to the era of the Truman administration, to an America before the interstate highway system, to find a time when the country had fewer cattle than it does right now. The reason for this historic decline can be traced directly to drought. To understand this cattle signal, one must first grasp how drought shapes the decisions of ranchers, a relationship that can seem counterintuitive until the mechanism is clear. When drought descends upon a ranching region, the initial response is often a forced liquidation. Ranchers begin to sell cattle they can no longer afford to feed. Pasture grasses wither or go dormant, and as drought reduces hay production, the price of hay spikes. A point is reached where the cost of keeping an animal alive through a dry year exceeds its market value. So, ranchers sell their calves, cows, and bulls. These animals go to market, often in waves that temporarily drive prices down as supply surges, only to drive prices sharply up in the following years as the herd begins its slow path to recovery. This liquidation cycle is a well-understood pattern. What makes the current situation so consequential, however, is the geography of the drought. As of early 2026, roughly 60% of the U.S. cattle herd was located in regions under drought conditions, including the southern plains, the southwest, the mountain west, and the southeast. When such a vast portion of the herd faces drought pressure simultaneously, the liquidation is no longer a regional and manageable event. It becomes national and structural. The price spike that follows a liquidation this broad is not a local market correction, but a multi-year national event that will affect every American who buys beef. The USDA's own projections for beef prices in 2026 and 2027 reflect exactly this scenario. They forecast record retail beef prices that will exceed previous highs, driven by the combined pressure of reduced domestic supply from the liquidation and lower import availability due to similar drought conditions affecting cattle production in South America and Australia. The dollar per pound figures at grocery stores are already starting to shift, but the full impact remains months away. This is because beef supply chains operate with a significant lag time between a reduction in the herd and the resulting movement in retail prices. Herein lies perhaps the most important aspect of the cattle signal as an indicator of drought, its recovery timeline. Rebuilding a cattle herd after a massive, drought-driven liquidation takes years, not months. Heifers must be held back from the market to be bred, and their calves must be raised to weaning age. The entire cycle, from a breeding decision to market weight beef, takes a minimum of approximately 3 years. This means that even if drought conditions were to improve dramatically tomorrow, the cattle herd would not recover to its pre-drought levels for at least 3 to 5 years. The drought's economic impact on beef prices will therefore outlast the drought itself by years. The damage being measured in 2026 will still be felt at the grocery store in 2028 and 2029, long after the weather patterns may have shifted. This is the critical insight that the cattle signal provides. It shows how the economic consequences of a climate event can be fully locked in before the event even reaches its peak intensity. The herd liquidation has already occurred. The breeding stock has been sold. The recovery timeline is already set in motion. Though El Niño has not yet arrived, its effects on American food prices, operating through the drought that already exists, are already baked into the future. Our focus now shifts to the Colorado River and to a silent sentinel on the Utah-Arizona border, Glen Canyon Dam. This 186-meter wall of concrete spans the river, holding back what used to be one of North America's most spectacular canyon systems. Behind it, Lake Powell was designed to stretch for nearly 300 kilometers through the eroded sandstone of the Colorado Plateau. But that was its past. At present, Lake Powell is sitting at roughly 23% of its full capacity. A visible bathtub ring of bleached sandstone extends far above the current waterline, marking the levels where the reservoir once sat, a stark monument to years of decline. This matters for reasons that extend far beyond the aesthetics of a shrinking reservoir. Glen Canyon Dam is one of the most important hydroelectric generation facilities in the American West, providing power to about 5 million people in Arizona, Nevada, Utah, Colorado, Wyoming, New Mexico, and Nebraska. The dam generates electricity using turbines that are driven by the pressure of water falling through penstocks, which are massive pipes running through the dam's base. That pressure is a direct function of the water's height above the turbines. A taller water column creates more pressure and generates more power. This reality raises a deeply concerning possibility. Below a certain water level, there is simply not enough pressure differential to run the turbines efficiently. The entire system is approaching a critical threshold. Below a certain point, known as the minimum power pool elevation, the turbines at Lake Powell simply cannot operate. This critical threshold sits at approximately 3,490 feet above sea level. By the spring of 2026, the lake's water level was dangerously approaching this line, a descent that had already caused a reduction in power generation. Trajectory models projected this decline would only continue through the summer drawdown season, unless a dramatic and unforeseen surge of inflow occurred. Yet, with the snowpack in the vital Colorado and Utah basins at mere fractions of their normal levels, the prospect of such a surge seemed vanishingly small. The available data all pointed toward a more probable and unsettling scenario: the continued depletion of this vast reservoir, raising the question of what happens when a system's foundational buffers are nearly exhausted. The relationship between energy and water along the Colorado River represents one of the most complex infrastructure dependencies in the United States. It is not merely that the river provides both water and power. It is that these two supplies are so deeply coupled that they create feedback loops, especially during a crisis. When hydroelectric output falls, the electrical grid must compensate by drawing from other sources, typically natural gas or power imported from regional markets. This substitution is not only costly, but may also be unavailable during the peak demand of summer, when air conditioning loads across the Southwest already place immense strain on generation capacity. At the same time, lower river flows directly impede the ability to move water through the elaborate systems of canals and aqueducts that serve Phoenix, Las Vegas, Los Angeles, Tucson, and dozens of smaller cities. The equation is stark. Reduced flow means reduced deliveries, which in turn leads to water restrictions, impacting the economy and quality of life for tens of millions of people. Further downstream, Lake Mead, the lower Colorado reservoir held back by Hoover Dam, was in a similarly precarious state. Sitting at approximately 30% of its total capacity, its low level had already triggered official shortage declarations under the framework of the Colorado River Compact. These declarations initiated mandatory cutbacks in water deliveries to Arizona, Nevada, and Mexico. However, the tiered system of reductions built into the compact was originally designed for a system experiencing only moderate stress. It was never conceived for a scenario where both major reservoirs would simultaneously be well below 25% capacity, all while being fed by inflows from a record-low snowpack. The established rules, it seemed, were proving inadequate for an unprecedented crisis, forcing a confrontation with what happens when the safety nets themselves begin to fail. In the field of systems thinking, there is a concept known as a threshold system. This describes a system that behaves one way above a critical point and a completely different way below it, where crossing that line can trigger irreversible, or at least very hard to reverse, changes. Lake Powell and Lake Mead are textbook examples of such threshold systems. As long as they remain above their minimum power pools, they generate electricity, store water, and provide a crucial buffer against drought. But once they fall below that line, they lose their primary function. Recovery is not a simple matter. Even if favorable conditions were to return, refilling the reservoirs is a process that would take years of above normal precipitation and runoff to achieve. This reveals that the danger is not just a temporary shortage, but a potential shift into a new, depleted state from which the system may not easily return. By the spring of 2026, both reservoirs were on trajectories aimed directly at their critical thresholds. This descent was being fueled by a snowpack that had, on April 1st, posted its worst measurement in recorded history. The vast infrastructure that tens of millions of people rely on for their water and electricity was approaching a boundary from which there might be no easy return. And what makes this situation so alarming is that it was all happening before the anticipated arrival of El Niño, the very climate pattern that forecasters expected would trigger the most severe conditions. The drawdown risk wasn't supposed to materialize at this speed until the El Niño forcing was well established. In essence, the system was running far ahead of its own worst-case schedule. While the water infrastructure crisis was approaching its thresholds quietly, measured in elevation lines on monitoring websites, the drought's other major consequence was already burning its way across the map in a far more visible and immediate fashion. This was the acceleration of the fire season. By May of 2026, approximately 1.8 million acres had already burned across the United States. While this figure would be notable at any point in the year, for early May, it represented a staggering 231% above the 10-year average for the same calendar period. To be clear, that is not 31% above normal, but more than triple the average burn area. The fire season had not just started early. It had begun with a pace and scale that would characterize an active mid-season in a typical year, all before the calendar period when it would normally be getting established. The strain on the nation's firefighting capabilities was immense. The National Interagency Fire Center publishes a metric called the National Preparedness Level, a scale from 1 to 5 that indicates the overall burden on resources. Level 5 signifies the full commitment of all available assets. By early May of 2026, the preparedness level had already been elevated to a point normally associated with the peak of the season in late summer. This meant that resources which would typically be in pre-positioning and training phases, such as tanker aircraft, elite hotshot crews, and suppression equipment, were already being deployed to active fires. The firefighting system depends on a resource pool that does not scale infinitely. There is a finite number of air tankers, a finite number of trained crews, and a finite amount of suppression capacity. This creates a dangerous deficit for the future, as capacity committed in May is no longer available for the historic peak of the fire season in July and August. A key tool for understanding this heightened danger is the Evaporative Demand Drought Index, or EDI. This metric has emerged as one of the most reliable predictors for fire risk, precisely because it captures the thirst of the atmosphere, its capacity to pull moisture from the landscape. When EDI values are high, the moisture content in living vegetation drops, even in regions that have not experienced a catastrophic lack of precipitation. This is because the atmosphere itself is drawing water directly out of leaves and stems, desiccating the fuel. Fire behavior under these high EDI conditions becomes extreme, characterized by rapid spread rates, high flame lengths, and a powerful resistance to suppression. In the most severe cases, fires can generate their own weather, forming pyrocumulonimbus clouds that can cast burning embers miles ahead of the main fire front, spreading the destruction in an explosive, unpredictable manner. Perhaps one of the most significant features of the 2026 fire environment was the geographic expansion of this extreme risk. the danger was no longer confined to its traditional domain in the western states. As we saw in Florida, the Southeast was experiencing drought conditions that transformed its normally wet-adapted ecosystems into high-hazard fire environments. Florida itself endured significant wildfire activity throughout March and April, with fires burning through pine flatwoods and palmetto scrub that had not carried flames of such intensity in many years. This unsettling expansion demonstrated that the crisis was not merely regional, but continental, as long-standing ecological boundaries began to blur under the pressure of these extreme conditions. The American Southeast does possess firefighting infrastructure, but it is an infrastructure designed for a fire environment fundamentally different from the one now being forged by persistent drought. This reveals a critical feedback loop between fire and drought, one that explains why drought conditions can intensify after a fire rather than abate. As a fire sweeps across a landscape, it does more than just consume vegetation. It fundamentally alters the soil itself. The intense heat infuses the topsoil with hydrophobic compounds, forming a water-repellent crust. This crust dramatically increases surface runoff and hinders infiltration, which means that any rain that falls on the scorched terrain flows away instead of soaking in. As a result, the groundwater recharge that these burned areas desperately need is significantly reduced. It can take many years for this hydrophobic layer to break down and for the soil to once again absorb water normally. In the interim, these burned regions contribute less water to the watershed, compounding the drought's impact on stream flows and reservoir levels. Fire also strips away the vegetative canopy that would otherwise regulate surface temperatures and preserve local humidity. In its place, a transpiring forest is replaced by dark, heat-absorbing bare earth or charred wood. This shift in the surface energy balance leads to greater sensible heat flux, which in turn causes local temperatures to rise and humidity to fall. These conditions become ideal for subsequent fires, even before the vegetation has had a chance to recover. In this devastating cycle, drought sets the stage for fire, and fire in turn deepens the drought. These are not sequential events, but simultaneous forces, each amplifying the others. And all of this, the record-breaking early fire season, the extreme preparedness levels, the fire's geographic spread into the southeast, and the feedback loops entrenching the drought is unfolding before the predicted El Niño has even arrived. The fire season of 2026 is not the one that forecasters warned of when they spoke of a super El Niño in late 2025. This is merely the prelude, the baseline fire season before the main event that was expected to drive the worst conditions has made its presence fully known. The United States, however, does not exist in a climatic vacuum. The same atmospheric dynamics responsible for this unprecedented drought in North America are manifesting in different ways all across the globe. These distant events are linked through teleconnections, vast atmospheric bridges that connect regional climates via shared patterns in large-scale circulation. It's a reminder that our planet's climate system is a single, interconnected entity. For instance, India's 2026 monsoon forecast is projected to be at just 92% of its long-period average, signaling below normal rainfall for a subcontinent of over 1 billion people, for whom a failed monsoon is an existential agricultural crisis. At the same time, Indonesia is contending with an unusually early dry season, which compresses its agricultural calendar and puts immense strain on food systems already struggling with population pressure. Meanwhile, Southern Africa is in the grip of a humanitarian drought crisis so severe that it has already prompted international emergency responses. These are not isolated coincidences. They are distinct regional expressions of the same underlying planetary scale pattern shift. They all point to the same building El Niño signal, the same realignments in tropical atmospheric circulation, and the same reorganization of Rossby waves that has produced the pattern lock over North America. This phenomenon is appearing simultaneously across multiple continents and climate zones. The US drought of 2026 is not a uniquely American story. It is simply the American chapter of a much larger global narrative. This context is critical for understanding everything from food price dynamics to geopolitical stability. When drought strikes several major agricultural regions at once, the world's normal market buffers the ability to buy from elsewhere when one region is dry begin to collapse. This is the pre-trigger global setup, and it leads directly back to a central, sobering question. If this is the synchronized planetary state, times before, times the main El Niño forcing arrives, what will the world look like after it does? At its core, El Niño is a periodic warming of sea surface temperatures across the central and eastern tropical Pacific Ocean. While the definition sounds simple, its effects on global weather patterns are extraordinarily complex and operate through mechanisms that can be deeply counterintuitive. El Niño does not simply reduce precipitation everywhere. Instead, it reshuffles the global distribution of rain and snow. As a result, some regions become wetter while others grow drier. The very same event can bring drought relief to Arizona, while simultaneously deepening a drought in Australia. Likewise, the same pulse of warmth in the Pacific can enhance winter rainfall in California, while diminishing summer monsoon rains in India. It is a global puzzle where one region's gain can be another's loss. For the United States in particular, strong El Niño events have historically produced two somewhat contradictory effects. They have been associated with increased winter precipitation across the southern tier of the country, including the southwest and parts of the southeast. At the same time, they tend to bring warmer and drier conditions to the northern tier, which is especially problematic during the crucial late winter period when snowpack accumulates. A super El Niño of the magnitude being forecast for 2026, with some models projecting sea surface temperature anomalies in the central Pacific to rise above 3 degrees Celsius, would represent one of the most powerful events on record. Such an event would be comparable to the historic El Niños of 1997-98 and 1982-83, both of which were linked to significant and highly complex patterns of regional drought and flooding across North America. Yet, a paradox sits at the heart of this unfolding story. The relationship between El Niño and drought is typically understood as a clear sequence. El Niño arrives, and drought follows. The causal arrow is seen as pointing from the Pacific Ocean's forcing to the continent's response. What the year 2026 has revealed, however, is that the system can reach record drought extremes times before times that arrow is even fired. The drought we have been witnessing, with its 1-3-1-year records, historically low snowpack, 99% coverage of Florida, and cattle herds at 7-4-year lows, all of this established itself during the neutral to early El Niño phase. This occurred before the tropical Pacific forcing had reached the magnitude upon which historical drought models were built, turning the established cause and effect relationship on its head. This timing is crucial because there is typically a significant delay between the peak of an El Niño event and its maximum drought impact in the United States. El Niño generally reaches its peak during the boreal winter, from December through February. Its atmospheric teleconnections, however, usually drive the most severe drought impacts in the US during the subsequent late winter and spring, with a typical lag of 6 to 12 months. Understanding this standard delay is essential for grasping just how profoundly anomalous the events of 2026 truly are. The consequences have arrived long before the cause has fully matured. Should the El Niño developing between 2026 and 2027 follow historical patterns, its most significant effects in the United States would likely arrive in the spring of 2027. Yet, this forecast comes as the spring of 2026 has already shattered records. This forces us to ask a different, more urgent question. The concern is no longer whether El Niño will bring drought, but rather what it will add to a dry spell that has already surpassed anything seen in 131 years of record-keeping. We are in uncharted territory, which is precisely why the next comparison is so compelling and so profoundly unsettling. To understand the potential scale of this challenge, we can look back to a historical parallel from 1877 and 1878. During those years, the most intense El Niño of the 19th century dramatically altered weather patterns across the globe. This shift led to devastating, simultaneous crop failures in regions as diverse as China, India, Brazil, and parts of Africa. The resulting humanitarian crisis, known as the Great Famine of 1877 to 1878, is estimated to have claimed between 30 and 50 million lives, marking it as one of the most lethal climate-driven disasters in human history. As historian Mike Davis explored in his book, Time's Late Victorian Holocausts, the meteorological event alone does not tell the full story. The climate change created a widespread vulnerability, but it was the intersection with colonial policies and market economics that ultimately decided who would perish. Of course, the purpose of this comparison is not to suggest that the world today faces a similar risk of mass mortality. Our global food networks, early warning systems, and emergency aid capabilities are far more advanced than they were in 1877. The true relevance of this historical event lies in its underlying mechanism. A powerful El Niño struck multiple agricultural heartlands at the same time in a context where those areas were already weakened by prior dry spells. The resulting stress was simply too widespread, too synchronized, and too severe for the response systems of the era to handle. Looking at 2026, even before El Niño has fully formed, we can see a disturbingly similar pattern. Major agricultural zones, like the US plains, parts of South Asia, and Southern Africa, are all experiencing drought simultaneously. The climate is presenting a structural parallel to 1877, though this time with better infrastructure, but a more intensely forced atmosphere. This raises a critical question. Will our modern institutions act on these trend lines before a threshold is crossed? Or will they, as has so often been the case, wait to respond to a visible catastrophe after the damage is irreversible? The 1878 analog is not a prediction. It is a stark illumination of our vulnerability. There is a crucial aspect of the current drought situation that often goes unmentioned in public discourse. The very systems that would typically bring an end to a drought of this magnitude are themselves compromised. Consider the American Southeast, including Florida, which is already enduring its most severe drought in 15 years. Historically, one of the most dependable forces for breaking such a drought has been the arrival of tropical storms and hurricanes. As these powerful systems journey inland from the Gulf of Mexico or the Atlantic, they can deliver immense amounts of rain in a very short time. A single hurricane making landfall can unleash the equivalent of a year's rainfall over a parched region in just 48 to 72 hours. While not all this water can be absorbed, much of it runs off too quickly to replenish deep aquifers. It effectively resets soil moisture, refills surface water sources like lakes and rivers, extinguishes wildfires, and disrupts the very atmospheric patterns that sustain the drought. However, the forecast for the 2026 Atlantic hurricane season, issued by NOAA and other research institutions, projects a below-average year. The probability of above-average storm activity is estimated at only 32%, a notable drop from the historical average of 43%. This suppressed forecast is, itself, a direct consequence of El Niño. The strong warming in the Pacific Ocean that fuels drought risk also generates increased upper-level wind shear over the Atlantic. This shear acts like a destructive force, tearing apart nascent tropical storms before they have a chance to strengthen into hurricanes. This creates a dangerous feedback loop, a kind of closed system for the most afflicted areas. The atmospheric pattern blocks rainfall, while amplified heat rapidly depletes moisture from the soil. The parched land then reinforces the hot, dry, atmospheric pattern. And now, the principal mechanism for relief, the annual influx of moisture from tropical systems, is expected to be weaker, precisely because the El Niño intensifying the drought is also stifling the storms that could break it. It seems every potential exit from this cycle is being closed off simultaneously. The very architecture of this drought appears more complete and self-reinforcing than any in recent memory. During the Dust Bowl of the 1930s, or the major drought of the 1950s, the relief mechanisms were merely delayed. Precipitation eventually returned. In 2026, the system is different. The relief is being actively suppressed by the same force driving the drought. The El Niño that is increasing drought risk is also diminishing the likelihood of hurricane landfalls that would bring relief to the southeast. The system is not just stuck in a dry mode, it is locked there by the very key that turned it on. This leaves us with a genuinely open question that no current model can definitively answer. How long will this lock hold? El Niño events are temporary. They have a life cycle where they peak and then decay. The great super El Niños, like the one in 1997 to 98, typically faded within 12 to 18 months of their peak. But this decay does not guarantee relief. The transition from El Niño back to neutral conditions, or to its counterpart La Niña, which is the most common outcome, simply reshuffles global precipitation patterns once more. For some regions, this brings welcome rain. For others, like the western United States, which is already in the worst drought on record, La Niña has historically brought drying conditions, not wetting. So, we are faced with a sobering reality. The primary relief mechanism is missing. The climatic lock seems complete, and the existing drought is still more than 6 months away from any conceivable large-scale shift in the weather patterns. This is the state of the system in the spring of 2026, a precarious landscape set even before the main trigger event has fully arrived. A profound gap exists between what is occurring and what is being discussed. The drought of 2026 has certainly generated data. There have been agricultural reports in trade publications, updates on water management from western states, and fire weather alerts issued by the National Weather Service. The records have been logged and the information has been published. But the integrated story, the understanding that all these individually reported fragments are expressions of a single system operating at an unprecedented level, has not broken through into the national conversation. This raises a critical question about our ability to adapt, because the gap between an event's severity and the public's response determines whether we act proactively or reactively. The fundamental problem lies in what disaster researchers call the absence of an event horizon. A hurricane has a landfall, an earthquake has its moment of rupture, a volcano has an eruption. These phenomena are defined by a clear before and after, a specific location, and a powerful, anchoring image. Drought, however, offers none of these things. It is a continuous variable, a creeping crisis that deepens almost imperceptibly. The day the Palmer Drought Severity Index crosses from severe to extreme feels no different from the day before it. The moment a 1-3-1-year record is broken looks exactly like the day that preceded it. Without an event horizon, there is no single crystallizing moment to anchor the story, and no definitive image to convey its true scale. The imagery we do have often fails to communicate the gravity of the situation. When we think of drought, the picture that comes to mind is often the cracked, parched mud of a dried-up reservoir bed. While we have seen countless such photographs, they carry a limited narrative power. Cracked Earth simply does not convey the concept of a systemic failure occurring on a continental scale. It lacks the dynamic, terrifying force of a wall of floodwater surging through a city, an image that immediately communicates immense and unstoppable power. The visual language of this particular crisis seems to fall short of its sprawling, silent reality. This narrative challenge is compounded by the fragmented nature of modern media. The story of agricultural impact is told in farming publications. The details of water management are confined to Western regional outlets. The threat of wildfire only breaks into national coverage episodically, when the flames grow large enough to be captured by aerial photography. Meanwhile, the effects on cattle markets are discussed in commodity trading circles, and the diminishing snowpack is a topic for outdoor recreation media and water specialists. No single venue is tasked with assembling all these disparate pieces into the coherent, systemic story they collectively represent. It is as though a great beast is being described by many observers, each looking through a tiny window that reveals only one part of the animal, but never the creature in its entirety. Beyond the structural issues in media, there is also the psychological dimension of a slow-moving disaster. Our human attention systems are finely tuned for acute, sudden threats, not for gradual accumulation over time. We are wired to notice sharp changes in our environment, but we tend to habituate to slow, creeping ones. A drought that intensifies by just a few % each week over many months fails to trigger the same primal alarm responses as a catastrophic flood or fire, even if its cumulative damage becomes orders of magnitude greater. This is the psychology of a slow disaster, and it operates simultaneously at the individual, institutional, and media levels. In a crowded landscape of information, the story of the drought must constantly compete for attention against crises that are faster, louder, and far more visually dramatic, even as its own aggregate impact continues to grow. Whenever a phenomenon of this magnitude unfolds with such quiet stealth, a natural human instinct emerges, to search for something hidden behind the curtain. The mind seeks not just a cause, but an intentional one, a lever being pulled, a system being controlled by an unseen operator. It is a search for a missing piece of the puzzle that could explain how something so massive can occur without a single, defining, explosive moment. It's an impulse worth examining with care, not to mock or dismiss it, but to understand what it represents. After all, skepticism, when applied with rigor, is one of the primary tools we use to approach a deeper understanding of the truth. The problem in this context is not that people are asking probing questions. The issue is that the real answer is often stranger, less intuitive, and in many ways more profoundly unsettling than the alternative theories being proposed. The scientific reality lacks the simple narrative of a villain or a switch that can be flipped. The theories that arise to fill this narrative void tend to cluster around familiar themes. One of the most persistent ideas involves the High-Frequency Active Auroral Research Program, better known as HAARP. This research facility in Alaska, which uses high-frequency radio waves to study the ionosphere, is frequently framed in online discussions as a kind of atmospheric control system capable of steering weather patterns and manufacturing droughts. Alongside this, established cloud seeding programs, which are real and used in various parts of the world, are often misinterpreted as proof of much broader, clandestine weather manipulation. Other arguments point to solar cycles, suggesting that a dip in solar activity is somehow reshaping global weather. And, as with many discussions of unusual atmospheric phenomena, the ever-present chemtrail hypothesis appears, proposing that aircraft are deliberately dispersing chemicals to alter the climate. On the surface, these explanations all share a common and powerful appeal. They offer something the complex reality does not: intentionality. They provide a narrative with an operator, a cause that feels proportionate to the immense effect being observed. The logic is seductive. If something this large is happening, surely an equally large and deliberate force must be causing it. But it is here that the laws of physics become an unavoidable and clarifying lens. The atmosphere above the United States is not a small or simple system. It is a vast and dynamic reservoir of energy. By rough estimation, the total energy contained within it is on the order of 10 to the 22nd power joules. The large-scale weather patterns that forge continental droughts involve colossal energy transfers, typically on the order of 10 to the 19th power joules. These are not abstract figures. They define the fundamental scale at which our atmosphere operates. They set the baseline for what it would take to meaningfully alter weather at a continental level. Now, let us compare that immense scale to the output of a facility like HAARP. At its absolute maximum, it transmits approximately 3.6 megawatts of radio frequency energy. This equates to about 3.6 million joules per second, directed into a small patch of the ionosphere hundreds of kilometers above the surface. For perspective, this output is comparable to that of a large car engine. While this is certainly useful for studying the physics of the ionosphere, it is not remotely capable of influencing the tropospheric weather systems far below, let alone locking a Rossby wave pattern over an entire continent for months. The gap in power here is not just large, it is effectively unbridgeable. We are talking about a difference of more than 15 orders of magnitude, a disparity so vast that it renders the notion of weather control physically implausible. To grasp the scale of the forces at play, one must consider the sheer energy involved. The difference between the output of a facility like HAARP and the power of a continental weather system is like comparing the energy in a single lightning bolt to that released by a major asteroid impact. This immense disparity raises a critical question. Could such a facility truly steer weather patterns across a continent? The physics suggests it is simply not possible, as the energy required far exceeds what could be generated. A similar, though distinct, challenge faces the concept of cloud seeding. This is a well-documented technology, not a theoretical one, that works by introducing particles like silver iodide into clouds. These particles act as nuclei, encouraging the formation of ice crystals that can eventually grow heavy enough to fall as rain or snow. While it can modestly boost precipitation by 5 to 15%, its success is entirely dependent on a crucial prerequisite: the presence of the right conditions. Cloud seeding needs clouds that are already rich with moisture and teetering on the edge of precipitation. In the drought of 2026, these conditions are conspicuously absent. The dominant atmospheric pattern, a stubborn high-pressure system linked to a displaced Bermuda High and a stationary Rossby Ridge, actively works against cloud formation. Air is sinking, warming, and drying out, while moisture is being pushed away rather than allowed to gather. In such an environment, there are simply no clouds to seed. The atmosphere is dry from the top down, and no amount of seeding can conjure moisture that fundamentally isn't there. Another line of inquiry points to the sun, suggesting its fluctuating activity could be the cause. It is true that the sun follows an approximately one-year cycle, with periods of lower activity known as solar minima, often corresponding to a slight reduction in the energy Earth receives. However, the magnitude of this change is incredibly small, on the order of just a fraction of a percent. This subtle dip is not nearly enough to trigger large-scale cooling, nor can it account for the specific regional drought patterns unfolding. More importantly, the current data directly contradicts this premise. We are in solar cycle 25, which has proven to be far more active than many forecasts anticipated. The planet is not cooling. Instead, global temperatures are charting some of the highest values in the instrumental record. While physical links between solar variability and regional drought do exist, they operate on scales and with magnitudes that bear no resemblance to the events of 2026. The chemtrail hypothesis shifts the focus from energy to composition, proposing that aircraft are deliberately dispersing substances to suppress rainfall. Once again, however, the theory collides with the problem of scale. To influence atmospheric processes over an entire continent, the mass of the required material would be astronomical, far beyond anything that could be deployed without being noticed. Such an operation would leave undeniable chemical signatures in the air, which would be readily measured by independent research institutions across the globe. Furthermore, the theory fails the test of geography. The drought's patterns do not align with air traffic density. Some of the most severely arid regions during this event see relatively few flights, while some of the planet's wettest areas lie directly beneath major international flight corridors. The evidence simply does not match the claim. What each of these alternative theories shares is a fundamental disconnect from both physics and observable data. They attempt to explain a vast, systemic pattern with mechanisms that lack the necessary power, the required reach, or the supporting evidence. It is in this gap between speculation and reality that the true explanation begins to emerge, not as a single, simple cause, but as a convergence of multiple, well-documented processes that are reinforcing one another. This convergence is not hidden. It is measurable in real time. The atmospheric configuration, with its persistent Rossby wave and westward stretching Bermuda High, is clearly visible in satellite data and atmospheric models. The principle of heat amplification, where higher temperatures dramatically increase the air's demand for moisture, is a direct consequence of thermodynamics, described by the Clausius-Clapeyron relationship, a concept understood for over a century. The soil moisture feedback loop, a vicious cycle where dry soils reduce evaporation, increase surface heat, and further suppress cloud formation, has been quantified in numerous studies. And the entire event is playing out against the backdrop of a long-term megadrought in the southwest, reconstructed using tree ring data that stretches back more than 1,000 years. The current anomaly, these record-shattering conditions appearing even before the expected push from an El Niño, is not speculation. It is what the data is showing us right now. This scientific explanation requires no hidden technology, no secret coordination. It only requires that the climate system operates according to the physical laws that govern it. Under current conditions, those laws are producing outcomes that feel deeply unfamiliar because they are pushing beyond the boundaries of our recent experience. In a way, this is what makes the situation so difficult to process. The conspiratorial narratives, while dramatic, offer a strange kind of comfort. They imply a world governed by intention and control, suggesting that if a hidden cause were found, it could simply be switched off. The real explanation offers no such reassurance. It describes a system evolving under its own internal dynamics, influenced by long-term shifts in temperature, atmospheric circulation, and land surface feedbacks. Perhaps most unsettling of all, it reveals how we could arrive at a moment where a 131-year record is broken not at the climax of a known climate driver, but in the quiet period just before it begins. This doesn't require a hidden hand. It only requires a system that has already changed so profoundly that its extremes no longer need to wait for a trigger. Every major drought in American history leaves behind a kind of blueprint. It is not a perfect map of the future, but a collection of patterns, warning signs, and consequences that can be held up against the present. When an event like the 2026 drought begins to fold, our instinct is to look to the past and ask, have we seen this before? If the answer is yes, then perhaps we can estimate where it leads. Perhaps, by studying the past, we can identify the ceiling, the upper limit of how bad things can get. To grasp the potential severity of what is unfolding, we naturally turn to the past for guidance. Yet, A careful examination of the closest historical parallels reveals a deeply uncomfortable truth. While each comparison shares significant overlaps with our present moment and explains a piece of the puzzle, none of them can fully encapsulate the situation. As we delve deeper, it becomes clear that the year 2026 is not simply a repeat of a past crisis. Instead, it appears to be something new. A convergence of multiple historical extremes, layered together into a configuration our world has never before witnessed. The most immediate and powerful comparison is, of course, the Dust Bowl of the 1930s. It remains the cultural and scientific benchmark for drought severity in the United States. The early data from 2026 is startlingly familiar. Palmer Drought Severity Index values for March and April at -7.85 and -7.5 respectively. The fall just shy of the most extreme months recorded in 1934 and 1936. Based on these raw index values alone, this event belongs in the same category as the most severe drought in modern American history. The parallels extend further. The geographic scale of the crisis is similarly vast, affecting huge swaths of the country at once, rather than being confined to isolated pockets of dryness. Early signs of agricultural distress, from collapsing soil moisture and declining wheat conditions to mounting pressure on livestock, also echo the first devastating stages of the Dust Bowl's assault on the Great Plains. However, it is here that the comparison begins to diverge in critical ways. The Dust Bowl unfolded in a world that was, on average, about 1 degree Celsius cooler than our own. While this may seem like a minor difference, its consequences in atmospheric physics are profound. Warmer air dramatically increases the atmosphere's thirst for water, a process that is exponential, not linear. This is governed by the Clausius-Clapeyron relationship, which dictates that for every degree of warming, the atmosphere can hold approximately 7% more moisture. This physical law translates directly into faster soil drying, intensified stress on plant life, and a more rapid evaporation of surface water, even with identical levels of rainfall. To put it simply, if the atmospheric conditions of 1934 were to occur in the climate of 2026, the drought would be significantly worse. The Dust Bowl, for all its severity, now represents a lower bound scenario, a glimpse of what drought could be in a cooler system, before the full force of today's heat multiplier was applied. Another crucial distinction lies in the context of each event. The Dust Bowl, while catastrophic, was a relatively discrete crisis that struck a system not already weakened by long-term aridity. The situation in 2026 is fundamentally different. It is emerging from within a multi-decade dry period in the American Southwest, a megadrought already recognized as the most severe in at least 1,200 years. This pre-existing condition is not a trivial detail. It fundamentally lowers the entire system's resilience. Reservoirs are already diminished. Deep soil moisture deficits are already in place. Ecosystems and vegetation have been under prolonged stress for many seasons. This means the drought of 2026 is not beginning from a neutral starting point. It is a new, intense pressure being applied to a system that is already profoundly depleted. This brings us to another set of historical analogues, the long-duration megadroughts revealed by tree ring data, such as the one that gripped regions between 1,500 and 1,560. These events are vital for our understanding because they prove the climate system can naturally sustain drought for decades, far exceeding anything seen in the 20th century. They represent the upper limits of natural variability, often driven by ocean-atmosphere cycles in the Pacific. Yet once again, the comparison is incomplete. These ancient megadroughts took place in a pre-industrial climate, without the influence of elevated greenhouse gas concentrations. The baseline temperature was lower, meaning the heat-driven amplification of drought, the very mechanism that so intensely dries out soils today, was not a significant factor. While the lack of rainfall might have been similar, the real-world impact in terms of ecological stress and soil moisture loss would have been less severe than what the same deficit would cause in our modern, warmer climate. Furthermore, our landscape itself is different. Centuries of modern land use, large-scale agriculture, and massive groundwater extraction from aquifers like the Ogallala have fundamentally re-engineered the hydrological system. These changes introduce complex feedbacks, creating a system that is not only warmer, but also more interconnected and arguably more fragile than the one that faced the droughts of the past. Looking for a global parallel, we might turn to the Great Famine of 1877 to 1878, a catastrophe connected to a powerful El Niño. This event triggered widespread, simultaneous droughts in places as disparate as India, China, and Brazil, leading to the loss of tens of millions of lives. It stands as a stark historical lesson in how a single climate pattern can synchronize environmental stress across the planet. But here too, the comparison falls short. The climate of the late 19th century was cooler than today's, even cooler than during the Dust Bowl. The atmosphere had a different baseline, one that had not yet been subjected to the cumulative warming that now serves to amplify such extremes. The 1877 event is an invaluable model for understanding synchronization, how different parts of the world can be struck at the same time. What it cannot tell us, however, is what happens when that global coordination is combined with the intense heat amplification of the modern era and layered atop an already existing megadrought. When we step back and consider these historical cases together, a clear but unsettling pattern emerges. Each analog provides a crucial piece of the puzzle, but only a piece. The Dust Bowl illuminates the potential for raw severity. The megadroughts of the 1500s demonstrate the climate's capacity for long-duration events. The Great Famine of 1877 shows how these crises can become globally synchronized. Yet, no single event in our records contains all of these elements at once. This leads to a difficult but unavoidable conclusion. There is no clean historical precedent for the year 2026. The crisis is not unprecedented because its individual components are unknown to history, but because their simultaneous combination, extreme severity, long duration, global synchronization, and heat amplification creates a challenge for which the past offers no complete map. A convergence of troubling signals is defining our current climate reality. We are witnessing a record-breaking lack of instrumental rainfall, a widespread collapse of regional snowpack, and the continuation of a mega drought that has already spanned multiple decades. Every deficit in moisture is being amplified by elevated baseline temperatures. This is all occurring within a locked atmospheric pattern that prevents any chance of relief, while a major climate-forcing event, El Niño, continues to build its strength in the background. Such a combination of factors is novel, and when confronting a system with no historical precedent, a fundamental question arises. Just how severe could the consequences become? Climate models are sophisticated tools, built to simulate a vast array of potential conditions, yet they possess known limitations, particularly when forecasting extremes. The most critical feedback mechanisms in a scenario like this, the intricate coupling of soil moisture, the stress on vegetation, and the interactions with fire, are also the most challenging to represent with complete accuracy. These processes unfold at small scales but can profoundly influence large-scale outcomes. Under the right circumstances, they can accelerate with surprising speed, potentially pushing the entire system beyond what the models are designed to predict. This introduces a distinct asymmetry in our understanding of the uncertainty. When models project the severity of a future drought, the range of possible outcomes is not evenly balanced. It appears there are more pathways for the situation to become dramatically worse than predicted than there are for it to be less severe. In essence, the upper boundary of what is possible remains less certain and is potentially far higher than the models might suggest. This is where the concept of compound risk becomes so vital. The drought is not one isolated issue, but rather a complex network of interconnected stresses, each one feeding into the next. For instance, losses in the agricultural sector diminish the food supply and drive up prices. The resulting increase in demand for irrigation places immense strain on reservoirs and groundwater supplies. As reservoir levels fall, the capacity for hydroelectric power generation is reduced. This, in turn, burdens electrical grids, which are already struggling to cope with the heightened demand for cooling during intense heat waves. A strained grid can then impact the very infrastructure needed to manage water, such as pumps, canals, and treatment facilities. These are not separate systems failing in parallel. They are deeply connected, influencing one another in real time. A disruption in one part of the network can easily propagate throughout, amplifying the consequences elsewhere. Simultaneously, another powerful feedback loop is intensifying. Wildfire activity, already outpacing seasonal norms, is altering the landscape in critical ways. By removing vegetation, fires change the surface reflectivity of the land and disrupt local hydrology. A burned landscape absorbs more of the sun's heat, sheds water far more quickly when it does rain, and becomes highly susceptible to erosion. Over time, these effects can force entire ecosystems into new, degraded states, diminishing their capacity to recover. Even if rainfall patterns eventually return to normal, groundwater depletion introduces yet another layer of long-term complexity. Unlike surface water in rivers and lakes, which can rebound relatively quickly after a wet season, aquifers respond on a much slower timescale. The depletion that occurs over decades of overuse cannot be undone by a single season of rain. When groundwater is heavily drawn upon to make up for surface water shortages, it can create a profound, long-term deficit that persists long after the drought itself has ended. This process effectively transfers risk from the present day into the future, eroding the system's resilience against the next inevitable climate shock. All of this is unfolding within a year, where global conditions are already under considerable strain. The world's food systems are intricately interconnected, and its energy markets are notoriously sensitive to disruption. Climate variability is now affecting multiple key regions across the globe at the same time. The drought in the United States, therefore, is not an event happening in isolation. It is a significant part of a much broader pattern of planetary stress. Perhaps most critically, this is all taking place before the peak forcing from the developing El Niño has fully arrived. This single detail matters more than any simple historical comparison because it fundamentally alters the timeline of risk. In past major climate events, the most severe impacts often coincided with the peak of the forcing mechanism. Yet in 2026, the system is already at or near record-breaking conditions, well before that peak is expected. This strongly suggests that the baseline state of the climate system itself has shifted. It implies that what was once considered an extreme condition is now achievable without the same degree of external push. When you combine all of these elements, the absence of a clean historical analog, the inherent limitations of modeling at the extremes, the interconnected fragility of our modern systems, and the anomalous timing relative to El Niño, an unsettling conclusion becomes difficult to ignore. We are operating in conditions that are, in a purely technical sense, unprecedented. This is not a rhetorical flourish, but a literal description of the situation. No prior event on record matches this specific combination of drivers, feedbacks, and baseline conditions. When that is the case, the question of where the upper limit of this event lies no longer has a clear answer. The outcome might resemble something we have seen before, only greatly amplified. It could follow a trajectory that diverges completely from all past patterns, or it could reveal entirely new behaviors and feedback loops within the climate system that we have not yet had the opportunity to observe. What we can state with confidence is this: if you are searching for a historical blueprint that can tell you precisely how this story ends, you will not find one. And that reality, more than anything else, is what makes this moment so profoundly different. Let us return to where we began, because that starting point is also the place to which this entire story keeps circling back, much like a system caught in its own relentless feedback loop. The United States has officially broken a 131-year drought record. It did not merely edge past it or tie it, it shattered it. The Palmer Drought Severity Index, the key metric climatologists rely on to quantify how deeply dryness has penetrated the soil, is posting values second only to the most devastating months of the 1930s Dust Bowl. An astonishing 60.92% of the contiguous United States is currently in drought, with nearly half the country experiencing conditions rated from severe to exceptional at the same time. Even Florida, a state almost climatologically defined by its humidity, briefly saw nearly its entire area fall under drought conditions. 8 western states simultaneously hit all-time record lows for their April 1st snowpack levels. The nation's cattle herd has shrunk to its smallest size since the early 1950s, and wheat conditions are collapsing across the plains. Reservoirs that were engineered to buffer against climate variability are now approaching thresholds they were never designed to reach. Fire activity is running far ahead of its typical schedule, and the hurricane season, one of the few natural mechanisms capable of interrupting a drought in the southeast, is forecast to underperform. All of this is already happening, but the most crucial part of this story, the detail that elevates this from a very bad year into a potentially historic inflection point. We typically understand our planet's climate through a predictable sequence. A large-scale signal, such as an El Niño or La Niña, first emerges in the Pacific Ocean. In the months that follow, its impacts unfold downstream across the globe. This fundamental order signal, followed by response, is baked into our forecasts, our agricultural planning, and our strategies for water management and disaster preparedness. It is the invisible calendar that organizes how we think about risk. What we are witnessing in 2026, however, appears to break that sequence. The impacts are already here, with records already broken, while the climate signal that was supposed to explain them is still quietly forming in the background. It is a deeply unsettling reversal, like hearing the sound of something shattering in the next room, only to then hear the object that caused it finally hit the floor. When cause and effect appear to trade places, it suggests the system is behaving out of order, and all assumptions built on that order become unreliable. The developing El Niño is at the heart of this paradox. Forecast models increasingly agree that it is likely to form, and may even become exceptionally strong. Some projections even point to the possibility of a super event, the kind of phenomenon that appears only a handful of times in a century. And yet, in operational terms, it is not here. The critical coupling between the ocean and the atmosphere that signifies a mature El Niño is still a work in progress. Despite its absence, the United States is already in the grip of drought conditions that, according to multiple independent metrics, are the worst in the continuous instrumental record. This leads to a question that is not a dramatic flourish, but a real, unresolved technical problem. If this is the state of the world before the main event, what happens when the primary forcing actually arrives? To understand the stakes, we must remember what El Niño does. In simplified terms, it redistributes energy and moisture across the planet. It shifts storm tracks, alters pressure systems, and fundamentally changes where rain falls and where it does not. In some regions, this brings relief from dryness. In others, it means the intensification of drought. Crucially, El Niño layers these effects on top of whatever baseline conditions already exist. And that baseline, right now, is not neutral. It is not even moderate. The global climate is already operating at the edge of the historical envelope under record stress. This means we are not layering El Niño onto a normal system. We are layering it onto a system that is already profoundly strained, which is where the idea of compounding comes into play. It is worth pausing here, because this is where the story shifts from a bad weather year into something structurally different. We can think of the ongoing drought not as a single event, but as a network of deeply interconnected systems. Soil moisture, agriculture, reservoirs, energy production, wildfire dynamics, groundwater, and entire ecosystems. Each of these components has its own thresholds, its own response times, and its own complex feedback loops. Under normal circumstances, these systems can absorb stress, they bend, but they do not break. But when multiple systems are pushed to their limits at the same time, they begin to interact in ways that amplify the strain. Agriculture provides the most immediate example of this cascade. When soil moisture plummets into the lowest percentiles, crops do not just suffer, they may fail to establish properly in the first place. This immediately reduces yield potential before the plant has even had a chance to grow. In response, farmers adjust their planting decisions, perhaps reducing acreage or shifting to different crops entirely. These choices, made in the present, ripple through commodity markets for months or even years to come. Lower production can lead to higher prices, which in turn influences global trade flows. Because the United States is a major agricultural exporter, these shifts do not remain a domestic issue. They propagate across the world. Simultaneously, reduced rainfall and snowpack mean less water is flowing into reservoirs. As their levels drop, so does the capacity for hydroelectric generation. Once certain critical thresholds are crossed, such as the minimum power pool levels at major dams, electricity generation can stop entirely. This forces energy demand onto other parts of the grid, often increasing reliance on fossil fuels or other, more expensive sources. The result is a rise in energy costs and a grid that becomes more fragile, especially during heat waves, which are themselves intensified by the same drought conditions. Then, there is the hidden crisis of groundwater. As surface water becomes scarce, both farmers and municipalities turn to underground aquifers as a last resort. Pumping increases dramatically, causing water tables to fall. Unlike reservoirs, which can be refilled by a few wet years, aquifers recharge over timescales of decades, centuries, or even longer. The overuse of this finite resource during a single severe drought can therefore permanently alter a region's future water availability, leaving a legacy that lasts for generations. Now, layer the dynamics of wildfire onto this already stressed landscape. Dry vegetation becomes abundant fuel. Extreme heat and low humidity dramatically increase the risk of ignition. As a result, fires start earlier in the season, burn with greater intensity, and spread more rapidly than ever before. These large fires do not just consume the land, they fundamentally alter it. They can change the composition of the soil, reduce the vegetation cover that helps retain moisture, and even affect local hydrology, making future rainfall less effective at replenishing the landscape. These are not separate problems unfolding in parallel. They are linked components of a single, cascading crisis. Each one feeds into the others, and all of them began to intensify before the primary forcing event, the El Niño, had even arrived. This is what makes the current moment so difficult to interpret using historical analogues. History gives us pieces of the puzzle, but it does not provide the full picture. The Dust Bowl of the 1930s shows us what happens when extreme drought leads to agricultural collapse and catastrophic soil erosion. But it occurred in a cooler climate without today's level of heat-driven evaporative demand. The southwestern megadrought of the 1500s reveals what long-duration dryness can do to societies and ecosystems, but it unfolded without modern infrastructure, globalized food systems, or the amplifying effect of anthropogenic warming. The Great El Niño of the late 19th century demonstrates how global climate synchronization can cause widespread famine. Each of these analogues is like a single lens, useful and informative, but ultimately incomplete. What we seem to be seeing now is multiple of these lenses overlapping at once. When we try to project forward from this point, the uncertainty is not just about how bad things might get. It is a deeper uncertainty about how the entire system will behave under conditions it has not experienced in the modern observational era. Our climate models are powerful tools, but they have their limits. While they excel at capturing average behaviors, long-term trends, and large-scale patterns, they are less precise when it comes to predicting extremes. This is especially true when those extremes are driven by complex feedback loops that operate at smaller scales or involve intricate interactions between the land, the atmosphere, and human systems. We are entering a new and uncharted territory, and our maps are still being drawn. In any complex system, certain interactions matter more than others, yet these are often the most difficult to predict. Critical feedbacks like soil moisture coupling, the stress on vegetation, and the interplay between fire and the atmosphere are notoriously hard to model with precision. Their behavior is non-linear, meaning they can amplify with startling speed. A tiny variation in the initial state can cascade into a dramatically different future. A sensitivity that creates what scientists call upper tail uncertainty. This isn't merely uncertainty about an average outcome. It is a profound lack of clarity about the worst-case scenarios. The distribution of possibilities is often skewed, suggesting there are simply more pathways for conditions to worsen than for them to unexpectedly improve. This uncertainty forces us to reconsider how we ask questions about the future. When we look ahead 6 months or a year, the most honest answer is not a single, confident projection. Instead, it is a spectrum of possibilities, one with a long, unsettling tail that stretches into outcomes for which we have no clear historical precedent. This brings the element of timing into sharp focus, because the timing of an event fundamentally determines our ability to respond. If the most severe impacts of a drought arrive after a clear signal, after an El Niño event has fully formed, forecasts have aligned, and official warnings have been issued, a window of opportunity opens. It may not be a perfect window, but it allows for action. Farmers can adjust their planting strategies. Water managers can make strategic decisions about conservation and release, and emergency systems can mobilize. But what happens when the impacts arrive before the signal? In that scenario, the window for a measured response narrows or vanishes completely. Decisions are still made, of course, but they are made based on assumptions that may already be dangerously out of date. Farmers must decide what to plant, or if they can plant at all, using soil conditions that are already at an extreme. Ranchers face the choice of holding onto their cattle or liquidating herds, a decision with consequences that take years to reverse. Meanwhile, water managers are forced to balance immediate needs against long-term sustainability, all without knowing how much deeper the deficit in water inflow might become. It is a quiet, unfolding drama that rarely makes headlines. These choices happen in offices, on spreadsheets, and in conversations far from the public eye. Yet they are the very actions that will shape the visible outcomes months or even years down the line. The most lingering aspect of this story is not just the severity of any single measurement, however striking the numbers may be. It is the fact that these conditions arrived early. The system did not seem to wait for its expected trigger. The response appears to be leading the cause. This observation challenges one of the foundational assumptions in assessing climate risk. the idea that the relationship between a forcing agent and the system's response is stable and predictable. It suggests that, under certain conditions, the system itself can begin to self-amplify, generating extreme outcomes without needing the full push from an external driver like a strong El Niño. If this is true, then our ability to define the ceiling, the maximum possible intensity of an event, becomes profoundly more difficult. In this territory, we are navigating without a map. We lack a clean historical analog for what is happening. Our models do not fully capture all the interacting feedbacks when they are pushed to their absolute extremes. And our policy frameworks were not built for a scenario where the worst conditions materialize before the warning signal has a chance to sound. All we are left with are the observations. Week after week, new data points arrive. Soil moisture maps, reservoir levels, crop reports, and fire statistics. Each piece of information tells a consistent story, reinforcing all the others. The system is under immense stress, and it was already under stress before the expected forcing fully arrived, and that forcing is still on its way. So, the question that sits beneath all the data, all the models, and all the historical comparisons is not whether this situation is significant. Its significance is already clear. The real question is, what does this become? If this is what the system looks like at the beginning, before the trigger has fully fired, then what will the peak look like? It is a question that has no clean answer, not yet. Perhaps the only answer will come in retrospect. When we look back and try to understand the moment the records began to break before they were supposed to, it is in that moment we may realize the true signal was not the forecast, but the data itself, arriving early, quietly, in a drought that looks like nothing, until suddenly it looks like everything.